And I might also be using the notion of a conjugate partition, lambda prime, which is writing down your partition, but in terms of columns. So in this case, it could be 3, 2, 2, 1, right? And the weight of the partition is just the number of boxes here, which is it. Okay, so that's the simple result. The difficulty was here to find the characters in the other cases where the Varna module is not simple, not irreducible. And it turns out that this class of representation still has very nice and interesting character formula. It's not a sum over all such sure functions, but sum over all partitions lambda with a length of lambda less than or equal to p. Since we have this class of representations, one can then study the properties of the Wigner quantum system for this OS1 to n solution in this class of representations, and that's what we did. And since you have characters, you can do you can study spectra, you can study some other things. By the way, the character here it just means that it's like a generating function for the weights. So the exponents of these variables are 1 up to Rn is the weight, and this is your multiplicity of the weight, the usual implementation of characters in this context. You may remember that our Hamiltonian was just an element of the Cartan subalgebra, so these are diagonal actions on weights. So it's almost trivial to go from a character expression to say a spectrum generating function. You just have to Hj on such a weight gives you h bar omega j times the corresponding weight vector. So we can just by doing this substitution go over from our character to a spectrum generating function in this case. And it's particularly simple in the isotropic case when all omegas are equal to one another, because then these sure functions, they're homogeneous polynomials, homogeneous symmetric polynomials, so a factor of that comes out, and what remains is your evaluation of your sure function at the value 1. This is well-known formula. This is just the dimension formula of GLN representations, of irreducible GLN representations. I've written it here in a notation that is given by McDonald, but I guess some of you would know it's a different way of writing, but it's explicitly known. I mean, here it's kind of generalized binomial. This is a conjugate partition, and this is the definition here. Cij is the context, so it means you just have to multiply all these factors and divide it by all the hook lengths of the corresponding diagram. And a hook length is just you take a box and you count the number of boxes of this hook here. So 1, 2, 3, 4, that's the hook length of this box. But okay, that's a classical formula for essentially the dimension of a GL, of a irreducible kind of dimension, GLN representation. So since it's so simple here, we can collect all these expressions and collect them to say the same power of t, and then we see that in this representation dt we still got usual equidistance energy levels with a shift again, and the multiplicities depend on this expression that we've just deduced here. In the case that p is equal to 1, one can check that the canonical commutation relations are satisfied in this representation, and then for the multiplicities of these energies one gets just the usual classical formula that you find in all textbooks essentially, and this is the generating function. For p equal to 2, we can work it out, and the multiplicities increase. Not going to write down the generating function, but that's something important now, I think. And then we also worked out the case that p is equal to larger than n minus 1. Again, use these explicit formulas and write down either spectrum generating function or write it down explicitly here. Maybe it's better to present these results in terms of a table. So I've taken n equals to 3, it's three-dimensional harmonic oscillator. P is equal to 1 is the canonical case, so the usual energy levels with well-known multiplicity. P equals to 2, you have just a shift in energy and multiplicities increase, and then the third case here, because there are only 3 distinct cases to be considered. P larger than 2, shift in energy, and multiplicity still increase. And that's sort of the first few values of these energy multiplicities. Now, apart, and this is more recent work that a student of mine did now. I'll try to be short because time is running out. We'll start it later, but okay, let me just say a few words about it. If n equals 3, one can also consider or try to define angular momentum operators. Canonically, this would be just Q cross P in case that your position and momentum operators satisfy the canonical commutation relations. Here they don't satisfy these, so we have to be a bit more careful, and they can be defined by anti-philitrizing like here. And in terms of our generators, they would take this form, so this epsilon JKL is just the usual Chilita symbol. Now it's a bit surprising that our compatibility conditions on their own, they do not lead to particular nice commutation relations, for example, for these M's here, for these operators. But if we work in a realization in this OSP1 to N, OSP16 realization here, then these operators do satisfy the usual commutation relations as in the canonical case, provided one works in the isotropic situation. So it means we are, in terms of algebras, we are dealing here with the SO3 subalgebra of the U3 algebra that I've shown you before. And in order to determine then what we call the angular momentum contents of these representations, one just has to consider the decomposition of your OSP, of your infinite dimension OSP16 representations with respect to this chain of subalgebras. Now, since we have the character, it should be possible to do this. The decomposition to SU3 or to U3 is simple because that's already part, in fact, of your formula. These S lambdas are just the irreducible characters of U3. But and to go from U3 or SU3 to SO3, this is a well-known, this can be done by a well-known generating function. So in Lincoln label notation, this is a generating function. This was, I think, first constructed by Sarah and Sharp and some other people. And it means if you expand this, and if you look at the coefficients of a to the power a, b to the power b, this tells you what is the decomposition of the representation with Lincoln labels a, b as an SO3 representation. So in this case, if we translate it into the partition notation that we've been using here, and the 1 and the 2 and the 3 are the parts of my partition, it means that this decomposition is governed or encoded by this generating function. So generating function actually means just expand all these denominators and then collect to similar powers of a1, a2, a3, and what you get in front of it in terms of the powers of Z and the powers of J tell you the SO3 and the U1, the energy content of that representation. And this is for the case, and this corresponds to the canonical case. P is 1, this is P is 2, and this is the general case. And that follows from that generating function I've just shown you there. In terms of pictures and multiplicities, so again, P1, this is the canonical case. This is the sort of angular momentum energy contents that you would see in standard books for a three-dimensional harmonic oscillator. So lowest energy is a multiplex with angular momentum 0. Next energy level you find a multiplex with angular momentum 1 and so on. So these are the multiplicities here. So for p equals 2, the difference is that you get more angular momentum multiplex, but only at this level, the first new one here, and in general, that's the situation. So it was, in fact, the study of these DP representations in OSP 121 that allowed us to generalize and study more of these properties here. And one can repeat and do the same for OSP 6N, which can then be interpreted as an n-particle 3D oscillator. I've written the form of these operators here. Let me just mention one thing without going into the details. The difficult step here is going from U3N to U3 plus Un in this decomposition. And although there's a formula for this, it's the coefficients you need for this decomposition are known as the Kronecker product coefficients, also appearing in Kronecker products of representations of the symmetric group. To compute these coefficients is still quite hard and difficult, and it was only due to a recent result of King and Welch who managed to write down a generating function for these Kronecker product coefficients that we managed to do this decomposition explicitly for a number of cases. Not for all cases in all generality, because computations still become quite hard as we managed to do it in some cases. One generating function is mentioned here, but I think that's too detailed to go to say something about it. Now, I intended also to say something about the other algebraic solutions and the properties that we have there, but I think my time is over, so let me skip it. It has also some interesting features, but let me go to the conclusions. So I had the honor, so to say, to be introduced to rate quantization by Tchavdar, because for me it has led to a number of interesting mathematical problems that I could deal with, because I knew some representation theory of superalgebras. So in particular, superalgebra already studied also by Palev, played a role in the topics that we treated, and since we managed now quite recently to be dealing also with a class of representations for which that were unknown before, or at least for which characters were unknown before, we managed to continue this program and in a way extend these canonical solutions under this OSP 1 to N case and get some interesting properties out of it. I haven't mentioned the properties of the U1N solution because I didn't treat that subject, but there the situation is quite different because we are dealing with finite dimensional representations. So it means we have also finite dimensional Hilbert spaces, spectrum of whatever physical operator you consider is thus finite, but it's very different properties from what we are used to. But even here there are some interesting aspects that can be observed. Thank you.